With this lesson, we're going to start studying chapter 4 in our book. This is really, this chapter is what we've kind of been building up to all semester long, learning about derivatives and how to do derivatives. All of that builds up to chapter 4, where we learn how to use derivatives to find key features of functions. We'll use derivatives to basically tell us how functions are behaving. We'll start in this section. We're going to learn about something called the extreme value theorem. Before we get there, though, I need to just show you some basic terminology. So that's what I'll do with this video, and then there will be some separate videos that I post that explain what the extreme value theorem is and how to do some computations based on that theorem. All right, so here let's just focus on learning a few new vocabulary words. Now, before you even worry about the definitions I have written at the top, let's just look at the graphs down at the bottom. And if I ask you on this graph, say on the bottom left, if I asked you to tell me what's the highest point on this graph, then I think you could find that pretty easily. The highest point is the point -2,4. Now on that same graph, if I asked you for the lowest point, well, that might be a little bit more of a challenge because there's not a lowest point, right? The graph goes down forever in both directions in this case. There is no lowest point. On the flip side, this other graph on the right, if I were to say, okay, here's a graph, show me where's the lowest point, you could point that out pretty easily. It's 0.1, -2. But this one happens to not have a highest point. When we talk about the highest and lowest point on a graph, we're talking about exactly what I wrote down up above. We call those the absolute maximum and absolute minimum for a function. Or sometimes we also refer to them as the global max or global min. So the absolute max of a function is its highest y value. The absolute min is its lowest y value. We could maybe say that a little bit more precisely. We could say something like f of c is the absolute max if f of c is greater than or equal to f of x for all x values in the domain of the function. Alright, so in other words, this y value f of c is considered to be the absolute maximum if it's bigger than all the other y values for that function. And then absolute minimum would be similar. So again, on this first graph on the bottom left, our absolute max would be 4, and our absolute min, there isn't one. I can even do a little bit more with describing the absolute max here. Instead of just telling what the absolute max is, I can also tell where it happens, where that max is achieved. The absolute max happens when x is -2. And then on this other graph on the right, again, I can tell pretty easily what the lowest point is. The lowest y value is -2, so that's my absolute min. Absolute min is -2, and it happens at x equals 1. But if I ask for absolute max, in this case, for this function, there's not one. All right, now another thing that we'll want to focus on in this chapter is not just the absolute max and absolute min. We'll also be looking at other points of interest. That could be something like this low point here. It's not the absolute lowest point, this point 1, -1, but it is the lowest point in the area. So if I just focus in on a specific area around that point, it's the lowest point in that area. Similarly, this point 3, 3 It's not the absolute max, but it's at least a high point on the graph. It's the highest point in the area. We have a name for those, and that's what I'll show you on the next slide. So those points that I was just talking about are called a local maximum and a local minimum. Okay, so f of c, this y value here, f of c is called a local maximum for the function if it's bigger than all the other y values, as long as you're focusing on an area near c. Now that little qualifier near c is an important qualifier. If I took that part away from the sentence, then I would basically be describing the absolute max. But when I say I want the highest y value for x values near c, what I'm saying is maybe a more precise way to say that would be in some open interval containing c. Open interval. And remember, when we say open interval, that means an interval that does not include the endpoints. Open interval containing c. Okay, that's what I mean when I say near c. So I can illustrate that here with this graph on the bottom left. If I look at some open interval containing 3, inside that interval, if I look at the graph, it's basically like I'm zooming in on just that portion of the graph and ignoring all the rest. If I zoom in and between the red lines and focus on just that piece of the graph and ignore all the rest, then I do have a highest y value in that area. All right, so this y value 3 would be a local max. And we can even tell where it happens. It happens when x is 3. So that's the local max. The local min is similar. Same idea. Now you're just looking for the lowest y value in the area. So if I draw some open interval, say containing the x value 1, and just kind of zoom in on the graph and focus on that piece of the graph, then within that region I do have a low point. The low point, or the lowest y value in that region, is -1. So that would be a local min. So we have a local min is -1, and that local min happens when x is 1. Alright, so that's local max and local min. So any of these places where we see high and low points, we can call them all max and mins, but we may need to be a little bit more specific. Sometimes we're dealing with an absolute max or absolute min. Sometimes we're dealing with a local max or local min. Now, this collection of all maxima and minima, you can collectively call them extreme values. So if I look back at this graph, 4, -1, and 3, those are all called extreme values for this function. Some of them are maxima, some of them are minima, but they're all collectively referred to as extreme values for this function. Or we may also call them extrema. Alright, so if I ask you what are the extrema for this function, you would say that the extrema are 4, -1, and 3. Extrema is a plural word. The singular version of that would be extremum. So if you say extremum, that's the singular form for extrema. Alright, so I can say that 4 is an extremum. I can say that 4, -1, and 3 are extrema. Alright, so that's some basic terminology. Max, min, extreme value. The other thing we need to look at before I send you over to the videos about the extreme value theorem. Oh, and now that you hear the name of that theorem, the extreme value theorem, clearly that's going to be a theorem that works with these extreme values, these max and min values. So you'll see that soon. But before we go there, one other thing I need to show you is we have a specific name for these x values where we could have extrema. Alright, so this kind of gets to the real, one of the main points to the chapter is how do we find these high and low points? And the way we find these high and low points relates to the derivative. Alright, so that's what we'll look at in the next slide. What we have here are 3 graphs, and I marked the extrema on all 3 graphs with the blue dots, and I labeled the x values where those extrema occur, A, B, C, D, and E. So what I want us to do is kind of see if we can come up with an idea of where our extrema should occur based on these pictures. So in these first 2 graphs, at the x values A, B, C, and D, let's relate this to what we know about derivatives. Alright, so can you fill in the blank here? At A, B, C, and D, what's true about the derivatives? At all 4 of those points, the derivative is 0. Right? Remember, derivatives give you the slope of the tangent line, and at every single one of these points, if I draw the tangent line will be perfectly horizontal. And if the tangent line is perfectly horizontal, its slope is 0. Alright, so that's something that we need to keep in mind when we're thinking about finding extrema of any sort. We want to know, where is the derivative 0? If the derivative is 0, then we might have an extremum there. But there's something else that could happen with our derivative that could lead to an extremum. If you look at the third graph, think back to something we talked about earlier in the semester. At this x value e, what's true about the derivative there? The derivative at e, whenever anytime a graph comes to a sharp point, we say that the derivative does not exist. And notice this point is an extremum. It's a local max, or we could even say, since it's the highest point on the entire graph, it is the absolute max. Whatever this y value here is would be the absolute max for that function. So we have 2 different things happening that could lead to extrema. We have the x value, or the derivative, being 0 at A, B, C, and D, and the derivative not existing at E, and all of those x values give us extrema. Those x values, whenever one of those 2 things happen, are called critical numbers, or sometimes critical points. So here's an important definition for us. A critical number of f is some number c in the domain of the function, in the domain of f, where either the derivative is 0 or the derivative does not exist. So we've got some number c. So c here is some x value, similar to the x values that we looked at up here. C is some x value in the domain of the function where either the derivative at that point, f prime of c, is 0, or the derivative at that point does not exist. Or instead of saying does not exist, we could it could be a scenario where we could say the derivative is undefined. All right, so this is the definition of a critical number. All right, one thing we need to make sure we understand here is that anytime the derivative is 0 or it doesn't exist, we have what's called a critical number. But we're not guaranteed to have an extremum at every critical number. In fact, there's one point somewhere on one of these graphs that is a critical number, but we don't have an extremum. Okay, so take a second, look back at these graphs, and see if you can find another critical number. It's one that's not marked or labeled, but if you look at the graphs, see if you can find somewhere that satisfies one of these two conditions, either the derivative being 0 or the derivative not existing. I'll give you a second to do that. So if you picked this x value right here, then you're correct. That x value is a critical number for that function. Okay, why is that x value a critical number? It's a critical number because if you look at the derivative at that point, the derivative is 0. If you draw a tangent line, the tangent line is perfectly horizontal there as well. So this is an example where the critical number, where we do have a critical number, but we don't have an extremum. All right, this is going to be a really important concept for us moving forward. One of our main goals in this chapter is to find all the extrema for a function. The first step in that process is to find all the critical numbers for the function. Once you find the critical numbers, then you need to figure out if those critical numbers give you an extremum or not. Sometimes a critical number could give you a max. Sometimes a critical number could give you a min. Sometimes a critical number will give you neither, like what we saw over here. So what you're going to be doing in the next few videos is you're going to see some examples of how you can find critical numbers. And then once you find critical numbers, you can use that information to find extrema. Now, the extreme value theorem is kind of a special case. You're going to start by looking at functions specifically on a closed interval. And you're only going to find the absolute extrema on that closed interval, the absolute max and the absolute min. Once you've done that with the extreme value theorem, then we'll move forward and work on finding all extrema for an entire function, not just over some closed interval. All right, so that's where we're headed in the next few videos. Before I send you to those videos, one more thing I want to show you. Let me just show you maybe a quick example of finding a critical number where we're not looking at a graph, we're just looking at the function itself. So what we're going to do here is find the critical numbers for these two functions. Now, what we've done on the previous slides, was kind of backwards from what we normally do. Normally, we do exactly what we're doing on this slide, where I hand you a function, and without knowing what the graph looks like, you have to figure out what's going on with the function. The first step in that is always finding the critical numbers. The previous slides, I was just using those to illustrate the concepts. There we started with the graph and then found the extrema, but this is more typically what we'll be doing. Alright, so we have no idea what the graphs of these two functions look like, and finding the extrema is one thing we can do to figure out what these graphs look like. The first step in finding extrema is always the same. We find critical numbers first. That will tell us all the x values where we might have a max or min. And again, remember, for critical numbers, we need to know where the derivative is 0 or where it does not exist. Alright, so in this first example, if we're going to find out where the derivative is 0 or where the derivative doesn't exist, first we need to know what the derivative is. This one's pretty straightforward. 3x squared minus 12x. And now to find the critical numbers, again, there's two things we need to check. First, are there any places where f prime equals 0? And second, are there any places in the domain of the original function where the derivative does not exist? I'll go ahead and answer the second part first. The derivative is just a polynomial. Polynomials are well behaved, their domain is all real numbers. There aren't any x values that could mess this function up. Alright, so that doesn't give us anything. But let's look at what happens when we try to figure out where f prime equals 0. So here we need to solve an equation. F prime is 3x squared minus 12x. We need to know, are there any places where 3x squared minus 12x equals 0? To solve this, the way we typically solve polynomial equations, if we can, we like to move everything to one side and factor. Here everything's off to one side on the left, and now let's see if we can factor. I could pull out, I guess I could pull out a 3x, but I'm just going to pull out an x and get the same answer either way. Factoring an x out, 3x minus 12 times x equals 0. So then one of these two factors must be 0. So either x equals 0 or 3x minus 12 is 0, which gives us x equals 4. So these two numbers here, 0 and 4, those are two numbers where the derivative would equal 0. F prime of 0 is 0, f prime of 4 is 0. So by definition, those are critical numbers. The critical numbers for this function are 0 and 4. Now remember what this means graphically. 0 and 4, these are places where if you were to graph this function, f of x, the graph would have horizontal tangent lines. The derivative would, being 0, means that the tangent lines at those two x values are perfectly flat. And those are two places where you might have extrema, or we might not. That would be the next step in the process, is once you find the critical numbers, then you need to test to see whether they give you extrema or not. Alright, we're not going to cover that in this video. The goal of this, or in this slide, the goal of this slide right here is just finding the critical numbers. We'll talk about how to find extrema in the coming lessons. This next example, g of x equals x minus the cube root of x. Same thing, we need to know, are there any places where the derivative is 0, or any places in the domain of the original function where the derivative does not exist. So the first step will always be finding the derivative. Before I do the derivative, I'll need to rewrite the cube root of x as x to the 1/3. So now again, this is a pretty straightforward power rule derivative. I have 1 minus 1/3 x to the negative 2/3. And then we need to answer the same two questions. Are there any places where g prime is 0? And are there any places in the domain of the original function where g prime does not exist? And coming back to our original function, the domain of our original function, the x values where this function works, is all real numbers. Here, x can be anything, and there's nothing that can mess that up. If I'm doing a cube root of x, there's nothing that can mess up a cube root either. I can do the cube root of a positive or a negative number. My domain here is all real numbers. So, if there are any places in the domain of the function where the derivative no longer works, that would be considered a critical number. So here, what I want you to do is go ahead and pause the video and see if you can answer these two questions on your own. Find where the derivative is 0, find if there are any places where the derivative doesn't exist, and then play the video and see if you were able to get it right. So starting on the left, finding where g prime equals 0, again, this is just practicing some algebra skills. We have 1 minus 1/3 x to the negative 2/3 equals 0. One thing I'll do here, and actually I'm going to come back up here to g prime. I think I prefer to write this as 1 minus 1 over 3 x to the positive 2/3. I'll do that here as well, just because I think, for me personally, it makes the algebra steps a little bit clearer on what's happening. So if I'm going to solve this equation, for me personally, there's multiple approaches you can take, but for me personally, what I would do first is move that 1 over 3x to the 2/3 to the other side of the equation. Alright, so you have 1 equals 1 over 3x to the 2/3. Another thing we like to do when we're solving equations, if there's a fraction, we like to clear the fractions. I can do that by multiplying both sides here by what's in the denominator. So now I have 3x to the 2/3 equals 1. Divide both sides by 3. X to the 2/3 equals 1/3. Now, I can wipe out this exponent 2/3 if I raise both sides to the 3/2 power. We do need to be a little bit careful here. If I'm raising both sides to the 3/2 power, raising anything to the 1/2 power, remember, is the same thing as the square root. Alright, so because I have this even number in the denominator, I'm doing an even root on both sides of the equation, which means I need to put in a plus or minus with it. So I have x equals plus or minus 1/3 raised to the 3/2. Those are the two x values, positive 1/3 to the 3/2 and negative 1/3 to the 3/2, where g prime will be 0. If you like, you could rewrite this 1/2 power as a square root. So that'd be the square root of 1/3 cubed, or 1/27. And we still have plus or minus that square root. Which way you write it doesn't really matter, they mean the same thing. But in the end, these two numbers here, positive square root of 1/27 and negative square root of 1/27, are both critical numbers for this function, because those are two numbers where if I plug them into my derivative, I will get 0 for my answer. Now coming to the second half of this, are there any places where the derivative does not exist? And again, it's, I think, helpful to look at the derivative the way I wrote it the second time, with instead of 1/3 x to the negative 2/3, if you write it this way, 1/3 x to the 2/3, it makes it really obvious that if x equals 0, I'm going to have trouble. G prime does not exist when x is 0, because if I do 1/3 times 0 to the 2/3, that's going to give me a 0 in the denominator. This is going to be undefined. So x equals 0 is a critical number for my function, because my function, my original function g of x, I can plug 0 into this function and get an answer. 0 minus the cube root of 0 is 0. 0 is in the domain of my original function, but then when I try to plug 0 into the derivative, it doesn't work. That's a place where the derivative does not exist. So by definition, 0 is a critical number. It's a place where in the domain of the function where the derivative does not exist. So in this example, we got 3 critical numbers. We got the negative square root of 1/27th. We got the positive square root of 1/27th. And we got 0. All 3 of those are critical numbers. And again, keep in mind what that means. Those are places, those are x values where if we were to graph this function g of x, those are the x values where we might have extrema. Those are kind of giving us the candidates for possible locations of extrema, maximum or minimum values. We don't know yet whether or not these x values will give us a max or min or neither, but that's where we're headed in some of our next lessons. All right, so that's the end of this example. What you'll be doing in the next few lessons is you'll be learning about the extreme value theorem. And in those videos, we're going to be looking at kind of a special case of finding extrema. We're specifically going to be focusing on finding the extrema for a continuous function over a closed interval. So in other words, we're just looking at some piece of a function instead of the entire function, and we want to see if we can find not just any extrema, but specifically the absolute max and absolute min for functions over a closed interval. So now you can go on to the next video, and those videos will go into more detail about how that theorem works.